Hello, everyone. Welcome to another episode of the Opsani webinar series. With me, I have Peter Nikolov, one of the founders, and Pavel Gorgiev, one of our principal engineers. And today we're going to talk about optimizing Java on Kubernetes. And we're recording this in a panel format. It's going to be quite interactive. And at the end, there'll be a few questions from the audience. And as always, I will moderate those questions, and Peter and Pavel will answer them. So let me just open up to both Peter and Pavel. Guys, I equate Kubernetes to a cloud-native technology, and Java to fairly old technology. Java has been around for 20 years. Kubernetes, I think, had just its 5th birthday. The question is, when did the unholy marriage of Kubernetes and Java begin in the first place?
Well, Amir, the key, I think that the marriage became, the marriage started when Kubernetes started becoming good enough to be used in enterprise environments. So when growth of Kubernetes started in large enterprises, that's where the need for running Java on Kubernetes kind of became natural. And I would say that probably happened around mid-2018.
And go ahead, Pavel. Sorry.
Yeah, in a way, it was inevitable. It was always going to happen. Just Java is so big in the enterprise world that if a technology like Kubernetes picks up enough of a pace, then Java's going to come to it. It's just a matter of time.
So the right answer is Java. The question is, what is orchestration technology? Very good. Now, I know that you've had extensive experience optimizing Java workloads for Opsani customers. What does it even mean to optimize Java on Kubernetes? What do we want to optimize, and how do we achieve the goals that gives the customers the benefits that they seek? If you could elaborate on that topic. First, what are the goals that the customer have with Java workloads, and then how do you optimize on that? I think that would be an interesting discussion.
Sure. So typically what customers want to see is they want to run their application in its fastest performance, ideally for the least amount of money. And what we provide kind of aligns very closely with that intent. Now, when it comes to Java, this actually gets a little complex since Java, well, being an enterprise product, has a large number of settings that can be configured, and then the full combination of settings there is probably not known to even the most experienced Java developers or operators. So where we come in is essentially look at all the runtime parameters available to or exposed by Java, and try to kind of find the best parameters that match your objective, whether this is skewed towards performance or towards optimizing for cost or anywhere in between.
And how do you, go ahead, Peter.
And to take this a step deeper is, in general, in cloud, you do have to optimize resources, amount of CPU, amount of memory, amount of replicas, and that goes for pretty much any language that is packaged as container and run on Kubernetes. What becomes even more important with Java is the additional virtual machines. So Java is a virtual machine. It has a lot of different mechanisms that work in order to keep it going. Things like the garbage collector, the way the heaps work. All of these things, they do, depending on how they're configured, they can cause significant differences in performance, more than 2x from what we have seen. And not only in the overall performance, but also depending on what the application does, whether it's, let's say, a transactional or web application where the response time is important, or if it's a computational application, the individual response time may not be important, but the duration, the total duration, and the efficiency, it matters. So in addition to what normally matters for all applications when they become cloud native, Java and Java virtual machine applications, which includes other languages like Kotlin and so on, has these additional requirements for optimizations to make sure that the behavior of the Java virtual machine matches the cloud and matches the use cases.
I want to drill down on something that Pavel said, which is that we discover Java parameters that we optimize. Can you talk about that mechanism? How do you do that discovery? Do you know those mechanisms a priori based on customers' goals, or is there a magic to the way Opsani discovers those components?
Right. So in terms of the things that can be optimized in a Java application, these are well known. The problem is the list is too long. The list is probably in the thousands. So just kind of, if you don't know what to look for, just trying random parameters and setting values for them, that's not going to get you anywhere. Now, there are people that are, they've spent decades, or probably for as long as Java has existed, tuning these things. So there are people that have the knowledge to be able to fine tune a Java application. From what we've seen, these people are, there's not a lot of them, because we've seen a lot of Java apps that are, let's just say, not very well tuned. So where Opsani comes in is we can take this basket of settings and feed maybe a portion of them to our product and our algorithms, and let it decide out of the variety of settings that can be tuned on Java applications, which are the ones that actually have effect on performance, and out of these, what is the actual value that is optimal for that application. So typically that will be like a very large space of combinations, and we try to do that in a reasonable number of tries.
And that is where our technology and using machine learning actually makes a huge difference. It is not an incremental difference. It essentially enables this, makes it possible. One of the additional things is that those settings that matter may differ from application to application and even from cloud to cloud. So different applications experience memory pressure differently. They have different response time requirements. So things that may not make much difference in performance in one application may end up making a huge difference in another application. So that decision cannot be made once and you just have a best practice of 5 settings that you want to optimize. No, you have tens and hundreds of settings, and then you have to figure out which of these settings actually matter for each specific application, and our product is able to do that.
Yep, absolutely. And just if I can chime in on that a little bit, it may not be obvious, but as Peter said, that there's no one setting to rule them all, or one set of values to rule them all. If there was, probably Java will ship with that with those settings out of the box, and that problem wouldn't exist in the first place. But it turns out that a lot of applications have different requirements, and what works for one application absolutely doesn't work for the next one. And we've seen that in practice. This is just not theory. We've experienced it in practice, where something that has a significant impact on application A is actually making the opposite impact on application B.
Okay, now I'm going to ask something that I think both of you guys alluded to, but I'm going to force the obvious question. Are there any easy wins? Like, for example, can we focus on garbage collection and say that value XYZ for garbage collection always improves application performance? I heard you guys say no, but I'd like to get I guess, a very clear answer on that, and some explanation as to why that is the case or that is not the case.
So the answer is mixed. The answer is yes and no. As Pavel said, there is no rule of thumb. Okay, always set the garbage collector to this and the GC time ratio to that. There is no such rule of thumb, and it's not even a small set of options that you have to explore. So that's kind of on one side. On the other side is, as long as you are optimizing per application, there are some things that we have noticed that are common in terms of parameters that matter. So the heap, and I'm sure we're going to talk more about the heap and containers and how that works in Java and Kubernetes specifically. The garbage collector in general, the selection of garbage collector and the basic tuning of it. So there's kind of the first, like if you have to only do 10, then there is a more or less well-defined set of about 10 parameters that will probably make significant impact on your application. So there is something that I perceive as out of the box. Okay, these are the parameters you should focus on. And again, that should be taken with a grain of salt because even if we have optimized hundreds of applications, the 101st application may have different requirements.
Yeah. So easy wins in terms of which settings matter, no easy wins in terms of what's the correct value.
Okay, but you've talked about maybe 10 applications, but you may not know how to correlate those, but that the space of 10 settings, 10 variables seems to be doable by a human. Why do you use machine learning? And why can't humans do the same task if there are only 10 variables?
Yeah, so first, it's not obvious which 10. Which 10 of the thousands are the ones that matter. And also, even within those 10, if you look at the number of permutations that you can, the problem space there, it's still very large for a human to explore. And when you couple that with the fact that this is a skill that is not very common amongst engineers, and it's also usually not a priority for people to spend their precious engineering resources on optimizing their application. That always comes after new feature, bug fixes, and optimization is somewhere in there, but definitely not in the top priorities. So yeah, this you could do that with humans, but it's a rare skill, and if you do have that skill in your organization, you probably have better use for it.
And yet, even there are 10, and we agree that 10 are not necessarily enough, but even if they're 10, when you look at all the possible values and the combinations, we're still looking in the hundreds of thousands of combinations, and that space quickly goes into billions and trillions of combinations.
Okay, I understand. Now, before getting into some of the more granular aspects of our conversation, I want to set the context. We are optimizing, and Pavel said that we're optimizing for the best performance, or least money for the performance that you choose. I don't remember the quite wording, but something like you have a performance goal and you deliver that at the lowest possible cost. Can you characterize what a typical customer sees by tuning a Java application, first by humans, then through machine learning?
So what typically customers see when they do manual tuning, they generally get improvements, I would say probably 10 to 15% to 20% may be typical. And that is a result of usually many months of work. And as Pavel said, you end up either having to find somebody who has the skill, or then you're probably looking at more months as the person acquires these skills. The one thing that ends up being tremendously frustrating for them and also for the managers is that it's a moving target. As your application changes with the DevOps approach and frequent releases, being able to optimize and try even 1,000 different combinations, you generally cannot do it while you're on the same release. So by the time you end up trying enough different options, the performance of your application has changed because there's new features, there's new library versions, and so on. So it is a moving target that you're after. What we have observed is that generally within a few months after search optimization, the goal has moved significantly. Again, more in the 20 to 30%. So that if you want to be able to do this with humans, that is a permanent work. There will be one or a couple of engineers for every service that are working only on that, and they have to work all the time. And the results are not that spectacular. 10 to 20% is a good result. The main thing is that when humans are doing that, they have some assumptions. Even the experts have knowledge of, okay, well, this is what should be done. Well, fact is, sometimes applications don't behave as the experts expect or what their expertise was built upon. So those are kind of in the human realm of tuning. It's very labor intensive, and the result is not that impressive. And it is a continuous process. You cannot stop it. It doesn't end. It has to be done all the time. When we apply machine learning to that, then we have seen some spectacular results. I would say on average in the 50% improvement. We have seen a few applications that went to over 70% improvement. And that was set up in a way that it does this automatically with every release. So as the process goes, even if the version changes in the meantime between experiments, the machine learning is able to carry portion of the learning and just doesn't get frustrated when things get pulled from under it. And is able to transfer the knowledge into subsequent optimization. So the result is that with machine-based optimization, you can get gains that are many times better in the kind of 50 to 70% improvement, and then keeping that going as you move to, like, your engineers add more code, new versions of Java come out, or you just simply run in a different cloud provider.
Yeah, and we've had cases where we've been working on applications that have been optimized internally by the performance team in an organization, and we've delivered results on top of that, which were kind of unobvious to a degree. When you first look at the settings, they don't necessarily make sense. Like on paper, that shouldn't be a good configuration, but then it actually works. And that's kind of one of the advantages of doing that with machine learning, is it will try things that normally a human may not even think of as viable. And kind of to put myself in the same basket, we did the same test internally in our organization, and we tried to optimize one of our services with, I mean, literally the best talent we had in the company. And then we set our algorithms to do the same thing. And I mean, we lost quite badly to the algorithms. And the result wasn't at all obvious. It was actually kind of fishy at first. We looked at it and said, well, that doesn't make sense. Why would you set these resources and these settings? But it actually, that was the best result, and by a margin, if I remember correctly, by over 70 or 80%. It was a significant number. Yeah.
I guess we need to test our algorithm against the Gary Kasparov of Java tuning, just to see if we can win that championship. But basically, if I parse through what Pavel, you said, and what Peter, you said, basically we're saying that we get somewhere between 3 to 5x above a human, because the machine learning algorithm has no intuition. As a result, it comes up with counterintuitive combinations that would normally escape people. And now we've talked about that 3 to 5x improvement. That's in performance. What does that mean for the business?
So for the business, what this means is
oh, Peter, you went on mute. So could you repeat that answer again, please?
Yes, what it means for the business is essentially 3 big things. One is the most experienced engineers that understand the system deep enough to be able to do optimizations are now available to do something that is productive and changes and adds features or capabilities. The second thing that it does, it clearly reduces costs, making sure that the cost of running the services is lower and continues to stay at the lowest possible value. So the finance department is happy, making sure that the margins of the company are working well. And there's knowledge that this is the cheapest it can get to meet that performance. And then the third thing is the things that come as a result of that optimization is you have an application that is more stable, better responsive with better customer experience. And what we have found is that after applications are optimized and stay in continuous optimization, they have significantly improved uptime as well.
Okay.
Yeah, and if I can expand on that, it also, people typically find a peace of mind knowing that their application is running at their optimal settings and at the optimal cost, which is nice to have when you look at your cloud spend bill and kind of wonder, well, that's a large number here. Am I using that money in a smart way? Is there room for improvement? So there's some peace of mind that comes with knowing that for sure.
And it is also complementary to the way people optimize in general. Normal kind of before cloud, the main optimization was, oh, you improve your code, you change the way your queries are formed, you change your algorithms, you restructure your algorithms to minimize the bottlenecks. And that is something that for now only humans can do, essentially, right? New code, change the way the code is done. But as a result, this is a very expensive undertaking. And with machine optimizations of the configuration, you get two kind of additional benefits. One is that everything that is possible to get from configuration and not having to do algorithm optimizations, you can get. So you get the 2 to 3x sometimes just for the asking, just turning on machine optimization, and you get that significant improvement that's almost impossible sometimes to get through code changes. And then similarly, you know that if you need additional performance, then there's no more configuration to be squeezed out. Kind of going back to what Pavel said, is you now know that you are running at the optimal configuration. So the only changes if you need more performance, you need to add more resources or you need to change your code. So that clarity in the engineering organization sometimes is really hard to get because people guess as they don't know the exact performance characteristics. So having the optimization in place allows you to have a clarity of deciding when you need to do some changes to the algorithm and kind of involve human to make these changes.
Okay, so I want to get a little bit more granular at this point of discussion and more technical. And I'm old enough to have been at Microsoft, at Sun Microsystems when Java was invented. So I was kind of there at the ground zero. Not that I had anything to do with it, but it was kind of cool being part of a company that introduced Java to the world. And as I recall, there was something when applications were written in Java, there was talk of black magic in terms of knowing how a particular application works and how you can tune it. And Peter, you mentioned about JVM heap sizes. Is that part of black magic, or what is the black magic, and what are the key components of the black magic that sway an application one way or another in terms of impressive performance gains?
Well, one way to start this, and yes, there's everything that's related to tuning Java applications, I think frequently is considered black magic exactly because it is hard to do. There's too many factors that matter, and then too many parameters that can be adjusted to fit these factors. So of course, it's not black magic. There is a good and predictable way in which you can do this. But even having understanding of the application and how the application works is not directly correlated to, okay, I know I need to just tune these two knobs, and when this dial goes up, I can turn that knob. That is exactly where machine learning, without the kind of assumptions that humans make, really solves the problem, because it doesn't really need to know the internal workings of the application. At the same time, is extremely persistent because it keeps trying, and also is very good at remembering what it has tried, and very good at finding correlations between factors that may appear unrelated to a human. Specifically, in Java, there's a lot of magic that happens in the virtual machine. There's the just-in-time compilation. There is just the whole heap management and the complexity of garbage collecting different objects with different life cycle. So even things that kind of look like the same operation, then that same operation happens second time, it may take a different code path, it may have a different performance characteristics. So there's a lot of complexity, and there's two ways to go. One way is to kind of do the white box approach and become extremely granular at the level of understanding of what works, and like tracing every single code line and every function call and understanding how they work, and trying to minimize it. And then the other approach is to say, I'm looking at this as a black box, and then you can optimize. You have to define what are the important metrics. Is it the response time, request per second, and so on, and then you uniquely tailor to make these configuration changes to meet these settings.
This is a good segue for ending the first part of this webinar, and we'll resume next month with part 2.